Welcome back to our video module on dynamics. Today, I'd like to pick up where we left off in our study of underdamped, overdamped, and critically damped harmonic motion. I'd like to revisit our cart problem, and as a little bit of a curveball, I've thrown in some numbers here in purple. So today we're going to look at each of these three systems, or examples of each of these three systems, solve the math so we can find position as a function of time. And the numbers in purple right here give us a mass, or tell us what our initial velocity is, what the spring constant and the damping coefficient are. And what I'd like you to do is I'd like you to solve for position as a function of time. To help you out, in I guess teal right here, and right here, I've given you the actual coefficients for these general forms of the equation. This is a nice little shortcut because, quite frankly, it takes some time to derive each of these. Before we get going on the solution, I'd like to cover something briefly. That's down here when we identified in green, orange, and red the three types of systems that we have for harmonic motion. We base it off this alpha, and that alpha came from this assumption. The assumption was the solution looked of this form. However, one of the things that we saw was we had a plus or minus here, so we have a quadratic. We have two solutions. Now, if we were really dotting our I's and crossing our T's, as soon as we saw that, we would have gone back through and given ourselves some sort of second solution. A good way to assume that would be some second exponential. That's not necessarily the solution, but it'd give us a really good start for solving everything. Now, that said, that also means that this alpha right here is not the same necessarily as these alphas up here. So now, put the video on pause, figure out position as a function of time for these numbers, and when we regroup, we'll compare our solutions. Let's walk ourselves through and see what we got here. Now, the first step that we did here is we found out which of the three scenarios are applicable for these numbers. And we find that b squared minus 4mk, it's a negative number, so we know that the system is underdamped. And if you recall, take a look at our green, our red, and our orange. B squared minus 4mk, that's going to be the red one because b squared is less than 4mk. So we know that the solution is going to be of this form right here. We take that equation, we find out what alpha is, negative b over 2m. We find out what omega is. So this gives us a start, but we still need to find out what A and B are. And for that, we use our initial conditions. Our initial conditions were that the original unsprung distance was where we started our time, so x of 0 equals 0. And our initial velocity was v of 0 equals v naught. Plug these into our equations, and we end up with this solution once we found all the constants. What I'd like to do next is I'd like to make this problem critically damped. And what I want you to do is I want you to change the mass so that the system is critically damped, and then identify what the equation of motion is. Go ahead and put the video on pause, see how far you can get. When we regroup, we'll compare answers. Now, to start off, we simply set b squared equal to 4mk. This is our condition for critical damping, and we find that the mass is 0.7 kilograms. On our next step, we'll solve for position as a function of time. Welcome back. We started off with an equation of this form, and we knew that because it was critically damped, we'll go to the red section, or I'm sorry, critically damped is the orange right here. We know it's going to be of this form. So we went ahead and used our initial conditions to find A and B, and our final solution is right here. X of t equals 5t e to the negative 20t. Now finally, what I'd like to do is, I notice that if I decrease my mass, I'm now at critical damping. If the mass is higher at 5, it was underdamped. So I'm going to lower the mass now down to half a kilogram. And I suspect that that should take us into overdamped situation. Let's plug in with a mass of 0.5 kilograms. Solve for position as a function of time. Before we get started, right here is the corrected equation which you'll want to use for solving the overdamped scenario. My apologies for any confusion. Go ahead and put the video on pause, and when we regroup, again, we'll see how we did. So welcome back. Hopefully you ended up with something like what we have here in purple. Let's take a quick walk through. First, we confirmed that what we had was overdamped, and in fact when we reduced that mass, that ended up pushing this whole value positive. So we have an overdamped situation. So we don't expect to see any oscillation, which means we expect to see all real values in the exponents. That said, we found alpha and beta as the two roots of our quadratic, or basically we just plugged it into our equations. We found that it was negative 30 plus or minus 10 root 3. I then took that up here, started off with our original equation, found that x naught, or x of 0 is 0, so a equals negative b. Then we used our initial condition of the velocity at time 0 is v naught. Two equations, two unknowns. We can solve those pretty quickly. We found that b was negative 1 over 4 root 3, a was 1 over 4 root 3. We plugged those in here, and we came up with a solution that satisfies our initial conditions and tells us the position as a function of time. Now, all that said, a couple things to be careful of when we do choose A and B. It doesn't matter which one is A and which one is B, which one's alpha and which one's beta. But what is important is we make sure that we keep the A and the alpha together and the B and the beta together, just so we don't get signs mixed up down here. Now, that said, today we've explored all three scenarios. We've explored an overdamped or an underdamped situation first, then we went to an overdamped situation, and we also did a critically damped problem. I hope this gives you a little bit of a feel of how we solve each of these problems. Now in this case, we gave you initial V naught and we asked you to solve. We just as easily could have given you a displacement, or we could have made two masses that are oscillating with one another. There's all sorts of ways we can play with this, but I hope that the cart example gives you a clear, intuitive understanding of what's happening at a really fundamental level. Thank you so much, and I'll see you on our next module.